right, here we go. Continuity is drawing the graph without lifting your pencil. Okay. Now, that's a pretty informal definition of continuity. So we're going to look at what do I actually need to say formally to have a continuous function. Now, we're going to talk about continuity at a specific point. Okay. So the first thing that we noticed is that there should be a point on the graph. F of A exists. Okay. That means that there is a point. It means there is a closed point on the graph. Okay. What's the second thing that needs to happen? If you're going to draw your graph into a point and then it's going to come out the other side, the limit as x approaches A from the left has to equal the limit as x approaches A from the right. Okay, so there's the statement. What does that look like? It means that the limit, right, the tail comes in on the left and it comes out on the right. Okay, but I need continuous. If I'm going to have a continuous function, then the point and the limit should be in the same place, which means that the point is equal to, now I'm going to combine these statements. Right, if the left and the right limits are the same, I can combine them. Okay, so what does that look like graphically? Well, it means there's a point, and it means the limit. The limit comes into the point and then it leaves the point, all in the same place. Okay, now that's not a very user-friendly definition, so we're going to write it a different way down here. We're going to say f of A equals the limit as x approaches A from the left equals the limit as x approaches A from the right. This sort of takes all three things into account. There is a point, there is a left limit, there is a right limit. They are all equal. If you have this statement, the function is continuous. So we're going to write the conclusion. If all three conditions are equal, then f of x is continuous at x equals A. Notice that I'm only testing one specific point. If all three pieces are equal, 1, 2, 3, then the function is continuous. Okay, so we have some vocab words that we're going to look at. Jump, point, infinite. Okay, in the first row, we're going to draw a graph that fits this type of discontinuity. So we're going to draw a jump discontinuity. Okay, most of you already said the word jump, so I'm going to assume you know what that means. Okay, now I'm not labeling the y coordinate, I'm only labeling the x coordinate. At x equals A. That's it. Okay. In row 2, we're going to write a limit statement that describes this discontinuity. Okay, we're going to do it in the user-friendly format. So we have the point, the left, and the right. Okay, so f of A equals the limit as x approaches a from the right does not equal the limit from the left. So in that statement, you're going to have to put the equals or the does not equal in the correct spot based on the picture that we are drawing. And I'm going to have to write a little smaller. Okay, hold on. Okay. The point equals the limit as approaches a from the right does not equal okay, there you go. The point and the right limit are equal, but they are not equal to the left limit. Okay? So this is a jump because why? Algebraically, what happened? The left and right limits were not equal. Limits were not equal. This is the part that created the jump discontinuity. You will have to pick out the correct vocab based on how the limit statements evaluate. Okay? So let's do a point. We're going to draw a point discontinuity. Okay? Now I'm going to add a word here. Sometimes we call this removable. I'm never going to have you choose between those two words, but depending upon what text you're looking at or the multiple choice that you have to choose from, you could see either of those words. They mean the same thing. Okay, now I'm going to put a point up here. It's still a point discontinuity. Why? Because the graph is missing a point. Here, I'm skipping a whole set of y values. Here, I'm just skipping over 1 point. Okay, so let's write down the limit statements, right? Parts 1, 2, 3, and what do we get? Okay, so f of a does not equal the limit from the left, the limit from the right. Okay. I'm going to write one more line underneath of it. Because these two things are the same, I can combine them to this. Right? If you notice the left and the right are the same, there's no reason you can't actually write them together. Because they're the same. Okay. How do I know I have a point discontinuity? There is a point because the point is not equal to the limit. The point does not have the tails coming out of it, right? Not equal, because the point is not equal to the limits. Can someone else tell me how you know that there's a hole in the graph? Factor would cancel. What else happens if you have a hole in the graph?
If there is a denominator, that might cancel.
Okay, denominator could cancel. Before that happens, what do you get when you plug in your number, PJ? 0 over 0. Yeah, you get 0 over 0. You've got that factor that reduces. That's what happens when you get a point or a hole in the graph. Okay, Infinite discontinuity, another word for that is vertical asymptote. We don't usually call it an asymptote discontinuity, but that's what it is. It's a vertical asymptote that's causing a discontinuity. Okay, so let's draw. And I'm going to draw this. I'm going to draw the two arrows in the same place. They don't necessarily need to be in the same place, but I'm going to draw them that way just because. All right. Limit statement. I'm going to write all three parts. Okay. F of A does not equal the limit as x approaches A from the left all right. Looks kind of similar to the point discontinuity. That's why I picked that picture. Okay. So now this depends. I could write this. This statement actually describes that picture because both of those arrows are pointing up, which means it's positive infinity. Okay? It's possible that you have arrows that point in different directions. Okay? It's possible that you get this first statement where f of A doesn't equal the limit from the left, doesn't equal the limit from the right. Okay? Alternatively, you could have asymptotes that point in different directions. But how are you going to know what kind of discontinuity is when all you're doing is looking at the limit statements? Okay? It is a infinite because how do you know there's an asymptote in your graph, a vertical one? A number over 0, yes. Okay, so number over 0. How else do you know that there's a vertical asymptote in your graph? What happens to your limit statement? What is your limit statement going to equal? There's only two choices. Infinity. Okay, what is the difference between point and infinite? Because the limit statements sure look the same. Okay, it matters how they evaluate. Infinite discontinuity because the limit statement, now left or right, positive or negative infinity based on what sides you're looking at, right? There's an asymptote because you got infinity. How do you pick that out algebraically? That number over 0. You're going to have to check your limit statements and then pick the right vocabulary that goes with it. All right, let's do a couple of practice questions. All right, here we go. First one. All right, so we're going to do x equals -3. I'm going to write my three-part definition. F of -3. I'm not actually evaluating yet. I'm just writing the first step down. Okay? The limit as x approaches -3 from the left equals the limit as x approaches -3 from the right. Okay? Simplify all three parts. Figure out where the equals and the not equals goes. Okay, so let's plug in -3. Oh, well, that tells me there's going to be a hole in the graph. Do the other parts just to be sure. Okay? Notice here that these two things are actually exactly the same statement. It's okay to combine them once you notice that they're the same. Okay. So I'm just going to do a little factoring, a little reducing here. We get 1 over 3, or 1 over x minus 3. Okay. So we get undefined does not equal, plug in 3, negative 3 again, negative 1 over 6 equals, okay, I'm still going to keep all 3 parts even though I showed my work once. Okay, what is it? A point discontinuity. Why? There's no point and the limits are equal. What does it mean when there's no point? And left and right are the same. So there is a point discontinuity. Not continuous because of a point discontinuity. There's my answer. At x equals negative 3, it's not continuous because there is a point discontinuity. All right, see if you can set up all 3 parts for x equals positive 3. All right. Okay. All right. I already know it's a vertical asymptote, but I have the left and I have the right. Okay, to the left of positive 3, none of them are equal. Okay. I did a little table in my head. Right, I put my table over here. I did the left and I did the right. That's how I came up with my infinities. I already know it's a vertical asymptote because I got a number over 0. So then I factored in reduced, and then I tested my function. 1 over x minus 3 to the left of 3, that's like 2.9. Negative infinity. 3.1, 1 over positive. Okay. Not continuous because infinite discontinuity. That is your answer. How do you know it was infinite? You showed the work that led you to that. All right, let's test x equals 2. X equals 2 is what I want you to test. X equals 2. F of 2. The limit as x approaches 2 from the left equals the limit as x approaches 2 from the right. Okay, I left off the blanks, guys. It's a piecewise. Pick which part goes where. Pick which part goes where. And then evaluate. All right. At x equals 2, that's the first part. So I get 5 minus 2. So I'm plugging in 2. To the left is 5 minus x, so that's 5 minus 2. To the right is the x squared minus 1, so that's 2 squared minus 1. So we end up with 3 equals 3 equals 3. Continuous at x equals 2. Why? Because the point and the limits were the same. All right, this is my answer. Continuous at x equals 2. Notice that the work is right there for me to see. 3, 3, 3. Okay. Let's try 3. Is g of x continuous everywhere? That means all real numbers. Is it continuous at every single x value? Well, I don't want to do that limit statement more than once, okay? So we're going to look at this. Is x squared continuous? Can you draw x squared without lifting your pencil? Okay, yes. All right, check. X squared is continuous. Is x squared minus 2x plus 2 continuous? Last time I checked, drawing a parabola, you can do that without lifting your pencil. Yes. Is 4 continuous? Do you draw a horizontal line without picking your pencil up? Yes. Okay. I haven't even made it to the continuity definition. All I did is I looked at each of these individual pieces and I was like, yes, I draw them without picking up my pencil. Now you have to consider x equals 1 and x equals 3. Those are the only two places that I could possibly pick my pencil up. Those are the two x's that you need to test. Okay? So x equals 1. F of 1. Okay. F of 1 equals the limit as x approaches 1 from the left equals the limit as x approaches 1 from the right. Okay. X squared minus 2x plus 2. Okay. Is it continuous at 1? 1 squared. 1 squared. One. Okay. Yes. Continuous at 1. Now check 3. I know there's not a lot of room here, so let's see if we can't do it. 3. F of 3. I'm just going to work vertically instead. The limit as x approaches 3 from the left. Five? You get 5? I get 5. No. It's not. I mean, the point and the limit aren't the same. Three from the right. 4 equals 4 does not equal 5. Not continuous. Okay, why? Point, jump, infinite. Which one is it? Point, jump, or infinite? Okay, who has an answer? And raise your hand. You have to tell me why. Look at which ones are not equal. I have a point, I have a limit, I have a limit. Which ones aren't the same? From the left it from the right it equals 4. From the left it equals 5. PJ? Jump. From the left it's 4. From the right it's 5. It's a jump. No, there's a jump. Okay. 2 left. Find the constant so that the function is continuous. Okay. Y equals x plus 1. Yes, the line is continuous. Good. Moving on. Y equals 3 plus ax squared. That is continuous because it's a parabola. All right. Check x equals 1. Right? It's a piecewise function. That's the only place that you could possibly now lift your pencil. You've already determined that each of the individual pieces are continuous. Now we have to check the one in question. Where do you switch? Okay, the point f of 1 equals the limit as x approaches 1 from the left equals the limit as x approaches 1 from the right. Of 1 is 2 is what? Okay. Let's see what we get. 3 plus a1 squared. Okay, 2 plus 2 equals. I don't need to actually write 2 twice. I can just take that piece here. A equals -1. A is a coefficient, guys. Okay? So I'm going to show you a little picture. That helps check your work. Oh, you can't. Okay, hold on. It's coming. It's not Desmos calculator. It's going to pop up. Oh, there it is. Got it. Okay. Here you go. There's your picture. X plus 1. Okay, x plus 1 to the left of 1. Now I need the parabola with a -1 coefficient. Look at that. Are they continuous? Yeah. What if you had a different a value there? Not continuous. You can check it by graphing it to make sure you can draw it by only getting one line, right? Do you draw that red right into blue without lifting your pencil? Yes. Okay. Try your last one there. Number 5, by yourself. put a little reminder here. X not equal to 2 is really x less than 2, x more than 2. That's what not equal to 2 means. So that top part, there really is the left and the right. So I can kind of evaluate them together. What's going to happen if you plug in 2? 2K. Okay. Now you evaluate that limit statement. Okay. 3. You get K equals 3.
Yes.
And then you can open up your delta math, right? If you don't remember your login, please ask me. Don't make a new account. Okay, so let's see. F of 2 equals the limit as x approaches 2 from the left equals the limit as x approaches 2 from the right. Okay. And evaluate each piece. Now this first part, when x equals 2, is just k. All right, now I do notice that these two statements are exactly the same. So I'm just going to evaluate it once. I do notice that it factors. Okay, now I'm still evaluating the limit here. Plug in 2, I get 3. The result is k equals 3 equals 3, right? The point, the left, the right, k is still equal to 3. Could you try graphing this in your calculator and tracing it to see what actually happens? Sure.